Welcome, everybody. Today we are very excited to have Tejas Srinivasan present their paper CLiMB, a continual learning benchmark for vision and language tasks. Tejas is a PhD student at the University of Southern California. He's helping to launch the world of continual learning into continual multimodal learning with this exciting new benchmark he's presenting today. I think we're all very excited to hear more about it. So Tejas, please take it away.
All right. Thanks a lot for that introduction, James. And thanks for inviting me to give this talk. So hi, everyone. I'm Tejas. I'm a second-year PhD student at the University of Southern California. And today I'm going to be presenting our recent work called CLiMB, which is a continual learning benchmark for vision and language tasks. Yeah, this paper was recently accepted into the NeurIPS datasets and benchmarks track, which we're very excited about. So yeah, I'll get started. Yep. Yeah. So a long-standing goal of AI has been the deployment of multimodal agents in the world that can interact with humans and help them with a variety of tasks. So as humans have like a bunch of different things that they want these agents to be able to do that require them to reason over multiple input modalities, these agents should be able to reason over these inputs that it's getting from these multiple different sensory modalities, and then produce responses or actions to complete the user's goal, right? Or request. So let's look at some current paradigms of how this kind of model deployment is being done right now in the multimodal space. So the first paradigm of vision language deployment is a single task fine tuning. And this is the most common paradigm that we have been using in the pre-training era. So here, basically, if you have a pre-trained vision language model and we want it to be able to solve a bunch of different vision language tasks, we fine-tune a copy of the model for each of these tasks. A very obvious downside to this is that you need to store a copy of the model for each task. And this becomes very expensive as you start scaling the number of tasks that you want to be able to perform. One solution to this is our next paradigm, which is multitask learning, where you have a single vision language model that is simultaneously trained to perform all of these tasks. And then this model can be deployed and perform all these tasks in the agent, right? However, when the agent encounters a new task that it has not seen before, it's not able to solve it. So this paradigm is very static, and the model can't learn new tasks that it encounters. So this leads us to our paradigm of interest, which is continual learning, where we have a pre-trained model, and then it is presented with a sequence of arriving tasks that are like arriving one after another. So first, you learn VQA, for example, visual question answering, then you do a visual reasoning task. And then after learning on a sequence of such tasks, you have a model that is like learn these tasks continually. And then it can encounter even more new tasks once it's deployed, right? So this is a more dynamic and continually evolving paradigm compared to the previous ones that we saw. However, while continual learning has mainly been explored in the vision and language communities independently, it's so far unexplored in the multimodal domain. So what are some challenges in this continual learning setting? So the challenges of this kind of multimodal continual learning deployment setting are: one, you need to be able to transfer knowledge that you've learned from previous tasks to learn new tasks. So similar to how in multitask learning, learning on several tasks at once aids the model in learning each task because there's like knowledge transfer between those tasks. We also want to see a similar effect in the continual learning paradigm. However, while we're learning these new tasks, we also don't want to forget tasks that the agent has already learned. right? Like once I learn to do common sense reasoning, I don't want to forget my ability to do question answering. And the other challenge is that when you're in a continual learning setting, or in like a deployed setting, you're not guaranteed to have all your modalities when you're encountering new tasks. Right? So you can have you can have both text and images. You can have tasks with both text and images as input, and the model is able to solve those. However, when the model encounters tasks that have only text inputs or visual inputs, the model doesn't really know what to do since it's only trained to perform with all the input modalities available to it. So this is a problem where we need to be able to perform tasks when you have only one or a subset of all the modalities that the model has been trained on. So this brings us to our contribution, which is CLiMB, the Continual Learning in Multimodality benchmark. So CLiMB is a benchmark that is designed to help researchers study these various problems that are discussed in the multimodal continual learning setting. More specifically, problems or learning in CLiMB is formulated in the following manner. So first, there's an upstream continual learning phase where the model is sequentially trained on a bunch of on a sequence of vision and language tasks. And then there is a second phase, which is a downstream low-shot transfer, where the model at any point in the continual learning phase can be trained on low-shot versions of tasks that have both the vision and language modalities. So for example, for this agent, it hasn't learned common sense reasoning yet. So we have the common sense reasoning, or low-shot common sense reasoning in the downstream phase as well. And we also have language only and vision only tasks, such as those seen in the Glue benchmark or ImageNet, COCO object detection, that kind of stuff. So the second phase is basically low-shot learning of tasks that may or may not have all input modalities. So this is what learning in CLiMB looks like. So, oh, I don't know why this emoji is so pixelated right now. So we have the CLiMB benchmark consists of 4 main components. The first are the multimodal and unimodal tasks that models in CLiMB are trained on. Second are the models themselves that are used for the continual learning, that are used in the continual learning setting. Third, we have the algorithms that help a model learn continually. And finally, we have our various evaluation metrics to see how the continual learning models are doing with respect to the various properties that we talked about before. So let's go through these one by one. So the multimodal and unimodal tasks. For the vision and language tasks, we have 4 main tasks right now, which are visual question answering, natural language visual reasoning, visual entailment, and common sense reasoning. So all 4 of these tasks require some different skill or some different understanding or reasoning ability for the models. Next, we have our language-only tasks, which include IMDb, SST, HelloSpag, physical interaction, and common sense QA. So these are tasks that we believe could be benefited from visual knowledge that the model has learned in the upstream continual learning phase. Since some of these tasks are sourced from video captions, movie reviews, and some others like common sense QA and physical interaction QA explicitly have to do with visual knowledge. And finally, we have vision-only tasks. So these are kind of standard, like ImageNet 1K, iNaturalist, Places 365, and MS COCO object detection. So one thing to note here is that this is only a starting point for CLiMB. Like these tasks only represent a starting point for CLiMB. CLiMB can be easily extended to include new multimodal and unimodal tasks. And our documentation includes instructions and guides on how to do so for other researchers. Yeah, continual learning models. So this is the second step, where in our learning setting, we have a task-aware setup where we have a pre-trained vision language encoder that has a task-specific output or classification heads for each task. So this is in contrast to the newer trend of having like sequence-to-sequence models that can generate any, that can be used across all tasks and generate any kind of input. Here we have a task-aware setup with a pre-trained vision language transformer. In our experiments, we use the ViLT model, which is the vision language transformer, which operates over patches of the image. Yeah. So basically, you have an encoder and classification layers for each model on top. All right, now let's get into the various continual learning algorithms that we have included in the starting version of CLiMB. The CLiMB code base is designed so that researchers can add in their own algorithms or modify the existing ones. But for now, I'll introduce the 6 algorithms that we have implemented so far. So there's 6 different algorithms. The first 3 are kind of intuitive ones. So the first one is sequential fine-tuning, where you fine-tune the entire model, which includes the encoder and the task-specific layers, on each task as each new task arrives. So this is an extension of the single task fine-tuning method or single task fine-tuning strategy to the continual learning setting. However, this is likely to cause a lot of forgetting in the model as the model parameters are being constantly overwritten as it learns new tasks. So it's going to forget previous ones. Frozen encoder. So here you only train you keep the encoder frozen and you only train the task-specific layers. This solves the previous problem of forgetting since all the shared parameters are frozen. However, you have much less learnable parameters, and your capacity for learning each individual task will be much worse. And as a middle ground between the two, we have a frozen bottom K, where you fine-tune only the where you keep the bottom K layers of the transformer frozen along with the input embedding layers, and you only fine-tune the top encoder layers and the task-specific layers. So here you have, so now you have shared parameters that are learnable, but they're much fewer than in the first case. In our experiments, we set K equal to 9. So 9 out of the 12 layers are kept frozen. And now we have 3 more sophisticated algorithms that are experience replay, elastic weight consolidation, and adapters. You guys are like the continual learning community, so I'm sure you're very familiar with each of these, but I'm just going to go through them anyway because they're in the slides. So in experience replay, you have a pre-trained vision language model that after learning each task, we store a small percentage of the training samples in a task memory buffer. So VQA gets like a small percentage of the training data in a replay memory. And then the same is done for each task that it encounters. Now, when learning a new task, we when learning a new task, we also learn the new task, but periodically we replay a batch from one of the previous tasks buffers. So every nth training step, you replay either a VQA mini batch or a NLVR mini batch, and this basically refreshes the model's memory of the previous tasks. Elastic weight consolidation is more of a regularization method where after learning a task, we store its model weights, or specifically the encoder checkpoints, since those are the shared parameters that are being tuned. And when you're learning your new task, you have your task-specific loss, but you also add a regularization loss, which is an L2 loss between the model's new weights and the last saved checkpoint from the previous task. So this prevents the model's weights from straying too far or drifting too far from the checkpoint that it found to be good for the last task. And finally, we have adapters, which are a very promising field of work nowadays. So here we insert new task-specific parameters into the transformer layers. So this is our standard transformer setup. So you have your transformer input going into the self-attention, and then the residual connection there and on, feed-forward residual connection there and on. This is the standard transformer that we're all known to, that we all come to know and love. So in adapters, they basically insert parameters within the transformer layer, and these adapters are basically like two-layer MLPs with not many parameters and downsampling. The key to adapters, however, is that when training the model using adapters, the transformer parameters are kept frozen, while only the adapter parameters are learned. So this prevents the issue of forgetting. So when I learn task 1, I only have the adapters for task 1 that are being learned. And then when I'm learning task 2, I swap out the adapters for task 1 with new adapters for task 2. And only the adapters for task 2 are being learned. So then if I were to swap back if I want to perform if I want to like perform or do inference on task 1, later I can just swap the adapter parameters from task 1 back into the model, and there won't be any forgetting. So this is a nice property. This is like the key to adapters right here. It also has much fewer learnable parameters than training the full model, so it's faster to train. And it manages to achieve comparable performance to full model fine-tuning, which was really surprising to me, but it's really cool. Yeah. The downside to adapters is that there's no cross-task knowledge transfer. So when I'm learning task 1, I'm only learning the parameters for task 1's adapters. But then when I learn task 2, I'm learning the adapters for task 2 completely independent of what happened from task 1. So nothing that I used that was, or nothing that I learned when I was training on task 1 is ever used when trying to learn task 2. So that summarizes our algorithms. So let me get into evaluation, which I think is maybe our biggest contribution. So here's our evaluation protocol for evaluating the different properties. And let's take a refresher on what these properties are. So one, we want models to be able to transfer knowledge from previously learned tasks to new tasks. We want to prevent forgetting of knowledge that it had already learned about previous tasks. And we want the model to be able to transfer in a low shot setting to unseen multimodal tasks as well as unimodal tasks. So let's look at our evaluation protocol for each of these. So evaluation 1, upstream knowledge transfer. So if I have a continual learning algorithm A, and I've learned I-1 tasks, right? And now I train the model on the ith task. Let's say the score is SA, all right? Now, in order to know how much knowledge is being transferred by learning on tasks 1 to I-1, I want to compare this to if I were to train our pre-trained model directly on task I. So without continual learning, if I take my model and I directly learn the ith task, I have some score, let's say as PT, where PT stands for pre-trained, directly learning that task with the pre-trained model. So how much knowledge am I actually gaining by going from SPT to SA? by having these first I-1 tasks in there. So let's look at this number line here. SR represents the random performance on the task. So for example, if I have MLVR, which is a binary classification task, then SR would be 50%. Now, SPT is what the pre-trained model has learned. So this red line represents the improvement of the pre-trained model over random. Similarly, SA is what the continual learning algorithm has learned, and the blue line represents the improvement of our continual learning algorithm over random. So the difference between the two, which is this green line here, represents the absolute improvement of our algorithm over the pre-trained model, and the relative improvement, which is what we call upstream knowledge transfer, is the ratio of the green line to red line. So mathematically, it looks something like this. So in the numerator, we have the green line. In the denominator, we have the red line, and this is represented as a percentage, basically. So this ratio represents the green to red ratio represents the relative increase in model performance due to the transfer of upstream knowledge, or due to the upstream transfer of knowledge from tasks 1 to I-1. Does this evaluation make? Oh, I guess people are on YouTube. So yeah, I'm going to take a second so that you guys can just like look at this, because it's kind of key to yeah, it's not a standard evaluation protocol. A lot of existing evaluation methods with like multiple tasks and stuff, they just like do averaging the scores or something like that, which I don't believe is the right way to look at what's actually going on.
Yeah, I think it makes a lot of sense. Obviously, I'm always a fan of more metrics and more ways to view something better, but being able to specifically tease and look at this difference of this, I think especially thinking of this as a transfer way is just a much, much, much better way to look at it. And then of course the opposite, you know, I assume the negative value of this can also show what happens if the opposite is true, where you've destroyed some of the
Where you
pre-trained
lose
knowledge,
knowledge.
right? Yeah, I think
Exactly.
this is a
Yeah.
really good way to look at it. So
Yeah. Thanks for pointing that out. That's actually something that I should have specified myself. So negative values of this transfer correspond to the continual learning algorithm actually doing worse compared to a non-continual learning setting. And small spoiler alert for the results, most of the upstream knowledge transfer of the described algorithms are negative. So, which isn't a complete surprise, but yeah. Yeah, cool. So I'll move on to the other two evaluation methods, and those are also like almost exactly the same thing as this. So the second thing is evaluating the amount of catastrophic forgetting that is happening in the continual learning setting. So supposing our model has learned the jth task here, right? And it has like some tasks before it, doesn't really matter how many. And then after learning this, the model's performance on the jth task after learning the jth task is the score here, which is SAJ. And supposing we continue doing continual learning, and then later on we encounter some task I, and then learn this ith task. And after learning task I take my model and I directly evaluate the model on the previously learned task J, right? So let's call this score I to J, S I to J, right? So this basically means if I were to take the model after the ith task and directly evaluate on the jth task, what would my performance look like? And let's go back to our favorite number line here. So after learning the jth task, my performance, the red line represents my performance on the jth task. The blue line represents my performance on the jth task after learning the ith task. So there's like, so we expect usually with forgetting that there will be a decrease in performance. And the green line here represents the absolute difference between these two, between the um, two performances, right? And we define forgetting as the relative decrease in the model's performance when I go from learning task J to learning task I. So once again, this is the ratio of the green line to the red line. That's the relative decrease. Mathematically, it looks like this. But yeah, these formulas are not very nice to look at because there's a lot of superscripts and subscripts. But I hope the visual explanation makes sense. Positive scores of transfer correspond to greater decrease in, greater increase in forgetting. So we actually want forgetting values to be lower. Yeah.
Don't worry about the subscripts. In continual learning community, we are unfortunately way too familiar with having
Yeah.
1 to 10 subscripts on one number.
Yeah. All right. So our final evaluation protocol is for the low shot transfer, and this is very similar to um, the first evaluation protocol. So after learning your ith task, ith upstream vision language task, your model is directly evaluated on a low shot either vision plus language or vision or language task, and we'll call this score. Yeah, I'm not going to pronounce this. And then we compare this to if our model were to be directly trained on this low shot task. So this is comparing again your algorithm A versus the algorithm, or no, well, the pre-trained model's performance. Same number line, pre-trained model's performance is, let's say, the red line. The algorithm's performance is the blue line. The difference, and when I say performance, I mean improvement over random. And the green line is the relative increase or decrease. So the transfer again is the ratio of the green to red line over here. Negative values correspond to negative transfer. So the model gets worse at low shot transfer by doing continual learning. Yeah. All right, so that sums up our various evaluation methods. Let me see how I'm doing on time. So let's go into our experiments and results. So we have 4 vision language tasks as mentioned previously, and we ordered it in this order. First, the model is trained on VQA, then NLVR, which is natural language vision reasoning. Yeah. Then it's trained on SNLI visual entailment, and finally it's trained on visual common sense reasoning. We have our ViLT-based continual learning model, so the ViLT encoder with the task-specific prediction layers on top. And we evaluate our 6 different continual learning algorithms that we have described. So the first is upstream knowledge transfer. Let's look at upstream knowledge transfer first. So how does continual learning affect the model's ability to learn newly arriving tasks? So direct fine-tuning, so this is basically our SPT score. If I were to directly fine-tune the pre-trained model on each of these tasks, this is what those baseline numbers look like. Now, actually looking at the continual learning results, we see for the first 3 algorithms, we see that more trainable parameters corresponds to better performance usually. I think there's like one case where that's not true. But basically sequential fine-tuning has some amount of negative transfer. Sorry, sequential fine-tuning has some negative transfer, but frozen encoder is much worse because it has far fewer parameters to learn from. 2 other important things to note here. Almost all of the transfers are negative, which means that all of them perform worse than if I were to directly fine-tune the model on that task, and directly fine-tune the pre-trained model on that task. And also, the second thing is that the transfer usually gets worse as we go farther in the continued learning. So so for sequential fine tuning here, for example, we have like almost no transfer here because like it's only just learning the first task. But then after we go from the first task to the second task, we see that the transfer starts to drop a bit. And then from there, once you go to the third task, the transfer becomes even more negative. And finally, once we go to VCR, the transfer becomes even more negative. So with these naive methods, it seems that um, as you as you're learning every new task, you're forgetting a bit more of the pre-trained models knowledge that is useful to generalize and learn new tasks. Um, these are the results for the three more sophisticated algorithms. So experience replay and EWC also do worse than our to have like negative transfer, but experience replay actually has a better performance than sequential fine tuning, which means that for some reason, while experience replay is designed to mitigate the forgetting issue, it's also helping the model for like transfer a bit better to the new task. This could possibly be due to um, uh, I'm not sure exactly why this is the case, but it could be due to some transfer of knowledge from remembering the previous tasks that's helping it perform better or slightly better on the new tasks. And finally, we have adapters. So these are our best method by far. Since the transformer parameters aren't being overwritten during the continual learning, the model doesn't have any of this loss of pre-trained knowledge that's happening with the other algorithms. So it's able to learn each of the tasks as if the other tasks basically haven't happened. Well, we did see that that is somewhat of a disadvantage due to the lack of cross-task knowledge transfer. But right now, these seem to be doing better than the other algorithms. So main takeaways: more continual learning hurts the ability to learn new tasks, and adapters do not show negative transfer compared to fine-tuning of the shared model parameters or the shared parameters. Yeah. So let's look at the results for forgetting. So how does learning new tasks affect the model's performance on already learned tasks? So here we'll be looking at the forgetting metrics. So here we compute, if you remember what the what the metric looked like. So it's the forgetting transfer from I to J. So we're gonna like basically compute these for each combination of I and J. And I'm not going to put everything in a table. So we have graphs this time, which are much nicer for looking at the trends. So let's look at this graph here. So on the x-axis, this is the upstream continual learning task. And on the y-axis, this is the forgetting of the previous tasks. So if I'm looking at the second column over here, which is task 3, I'll be looking at the forgetting of the previous tasks, which are NLVR and VQA with these different algorithms. So after learning, so let's start with task 2, NLVR. So after learning NLVR, this is what the forgetting of VQA looks like. We see that sequential fine-tuning, I'm not sure if you can like make out the orange dot over here. The sequential fine-tuning and EWC seem to be doing the worst. Frozen bottom 9 and experience replay do better. So for frozen bottom 9 has fewer shared parameters that are being learned, and experience replay explicitly tries to combat the forgetting issue by replaying training steps from previous tasks. And at the bottom, we have frozen encoder, which has no frozen encoder and adapters. Both methods have no learnable shared parameters. Now, after learning the third task, which is visual entailment, the trends continue to look kind of similar. EWC does a bit better this time. So EWC uses a regularization loss to mitigate forgetting. And finally, after learning the final task, which is VCR, where we look at the forgetting of each of the previous tasks, we see that VCR causes a lot of increase in the forgetting. This is likely due to a task-specific trick or hack that is used to learn VCR, where bounding boxes were directly drawn onto the images. So the main takeaways are more fine-tuned parameters, more forgetting. Experience replay does better than weight consolidation. Adapters do much better than both because they do as well as freezing the encoder on the forgetting while also doing learning each of the arriving tasks better, as seen in the previous slide. And finally, the forgetting gets more severe after common sense reasoning. And this indicates that task-specific hacks that are frequently seen in the single task fine-tuning paradigm do not generalize to the continual learning setting because it's going to hurt other tasks. And finally, let's look at our experiments and results for the downstream low-shot transfer. So let's first look at low-shot transfer to unseen vision language tasks. So in the x-axis here, we have the ith task. Sorry for my mistake. This shouldn't be 2, 3, and 4. It should be 1, 2, and 3. And on the y-axis, we measure the low-shot transfer to each of the tasks that we haven't seen yet. So for the VQA column, I'll be looking at the low-shot transfer to all three of NLVR, visual entailment, and common sense reasoning, since all of those are unseen after the first task. Yeah, so here we only compare the algorithms that do have like learnable shared parameters. We see that so the main thing to note is on the y-axis here, everything is negative. So this means that continual learning always hurts the model's ability to transfer to unseen low-shot vision language tasks. And it kind of stays that way throughout, basically. So low-shot transfer is always negative. And this is very unsurprising because even in our first set of results, we saw that continual learning hurts the model transfer, even when we have all the training data available. So it's not really surprising when we only have a fraction of the training data available that this trend still holds true. Now let's look at the low-shot transfer to unseen to vision-only tasks. So here, our model is provided with a simple language prompt. This is an image alongside the actual image, and it's trained to do image classification or object detection. So ViLT achieves good low-shot performance on the vision tasks, like the absolute scores are pretty good. However, we're still seeing that the continual learning transfer is negative. So let me explain the graph again quickly. So on the x-axis, we have the model checkpoint after the ith upstream continual learning task. And on the y-axis, we have the low-shot transfer to our task. So here we have the results of ImageNet when trained with 16 shots per class and 32 shots per class. The trends are pretty similar. We also see that NLVR2 and VCR have more of a negative effect, especially VCR over here, if you see, like this decrease right here. Again, not very surprising, given that, or it basically reaffirms what we said earlier about task-specific tricks, such as those that we use for VCR, hurting the model's ability to generalize to new tasks. And finally, we look at low-shot transfer to language-only tasks. So here we have to spend a bit of time adapting ViLT for NLP tasks. There's a few challenges here. One is what should the visual input be for the language for the language-only task, since there's no like actual vision input in the data set itself. So we tried a few things like giving like just Gaussian noise, or giving or making the or giving like a zero image tensor, giving a black image. And eventually what we found out worked best was to average a bunch of, was to average images from the entire MS COCO set. So the model still sees an in-distribution visual input, since MS COCO is included in the ViLT pre-training corpus. So this visual adaptation seemed to work best. We had to extend language position embeddings. ViLT is designed only for sequence lengths up to 40, but most language tasks have much longer sequences, so we had to extend the position embeddings. And we also tried another method where where rather than using the word embeddings from the ViLT model, we replaced the input embeddings with word representations. And this also seemed to, rather, this is another model that we compare against ViLT, where we basically look at like do stronger language priors in the model representations, help the model generalize to language-only tasks. Yeah, so looking at our results here, we see that upstream continual learning helps sometimes. So the dashed lines correspond to the no continual learning setting. And on the y-axis, actually, we have like absolute accuracies here so that we can compare the ViLT and ViLT-BERT models to each other. So the dashed lines correspond to no continual learning, and the other lines do correspond to continual learning. We had to run multiple runs since it's a low shot setting. ViLT sees negligible differences. So that's comparing the blue and the pink line against this green dashed line over here. So on some tasks, it does better, like SNLI visual entailment we see. Or like the task point after visual entailment does better on SST2 over here. And especially with ViLT, so ViLT-BERT is the blue dashed line, and the continual learning models are the green and the orange lines. So here we see like a pronounced improvement here, in both the 16-shot and 32-shot case. The visual common sense reasoning task again seems to be hurting the model. So here we see like the negative performance on SST after learning the VCR task in the upstream stage. And we also have multiple choice tasks in our language-only CLiMB dataset collection. So these include common sense QA and HelloSwag. And yeah, common sense QA and HelloSwag, and the model performance the low shot transfer is not as good with continual learning in those cases. So in conclusion, we proposed CLiMB, which is a continual learning benchmark to study continual learning in multimodal settings. It's an extensible community tool, so we hope that people interested in continual learning, like you guys, will use this tool to study different tasks, different model architectures, and continual learning algorithms that can help models perform better continual learning in the multimodal scenario. We also run several experiments and show that existing continual learning algorithms fail at generalizing ViLT to sequences of multimodal tasks, enabling low shot adaptation. And yeah, overall, there's a lot of work to be done in this space. However, there are some promising results as well, especially with adapters, since they're most effective at preserving the pre-trained model knowledge. So the upstream knowledge transfer isn't hurt as much as fine-tuning the full model. And also, of course, in terms of how much better they are at forgetting, at mitigating forgetting than the other algorithms. And yeah, overall, we feel like there's a need for new research, new continual learning strategies, algorithms, models that can tackle this challenging multimodal setting. I know that this community is like very interested in continual learning, and I'm sure this benchmark will, or I hope this benchmark will provide an interesting environment or playground for you to like look into different questions in the multimodal continual learning space. And finally, I'd like to thank my co-authors. So the people with the stars, which is Tingyi and Leticia, and my advisor, Jesse Thompson. We are from the Glamour Lab at USC. And yeah, also our other collaborators, Yorgos and Mohammed. And yeah, thank you. Thanks for listening to this talk, people who showed up. We have our repository here for CLiMB. So we have extensive guides on adding new algorithms, adding new models, adding new tasks, and how to do the training. So if you're interested in these like multimodal continuing learning challenges that I've talked about today, feel free to pull our repository or make a fork or whatever. If you have new additions to the CLiMB benchmark that you want to make, like if you add new tasks, just send us a pull request. If you have any issues, you can open issues. And yeah, that's kind of it from my side. Thank you.
Great. Thank you, Tejas. I thought you did a really good job. The metrics, especially, I think were very intuitive, well explained, and motivated. And yes, time for question time. Yeah, you can go ahead and unmute, Chris, if you would like to ask your question.
Sure. So nice talk, and I absolutely agree with you that we should be doing more work in multimodal. Just as a comment, we put this out. I think in ECCV 2020, we did VQA, but not nearly as comprehensive as you. We only did natural language, or like a natural image data set, and Clever. And would encourage you to take a look at it, because we got really interesting results with Clever, where we actually saw like a curriculum of the tasks. Like we were looking at it more like in terms of the tasks within the VQA space, right? This kind of test, this kind of test, because VQA does many kinds of tests. We actually got some very interesting results where we saw like curriculum effects with Clever.
I do remember this. It's like yes, no versus some other type of questions, right?
I don't quite recall what the order is, but you mean what is Clever has all these reasoning questions, and like certain classes, whenever we ordered them in a certain way for learning the sequence, right? Because if you're learning, you got to somehow impose some sort of non-IID ordering. We had these interesting effects, but I thought, anyways, I just wanted to mention that. But my comment was about. Did you try training a single system to do all tasks in an offline way rather than in an incremental way? Because what I was worried about is, in my own work, I've seen if the model has insufficient capacity to memorize, so basically if you were to brute force it and memorize everything, like it doesn't have enough performance. If you saw that you trained it on all the tasks and it was universally worse than every one of the individual tasks, right? Then that would suggest you didn't have enough capacity to learn all the tasks. And so rather than measuring forgetting, you might just be learning not forgetting in terms of this is an unwanted thing, but more of a it had to forget because it didn't have enough capacity to do it.
Yeah, we didn't have like a multitask, like a top line, I think is what you're asking for, like a top line experiment.
Yeah.
We didn't include a multitask top line experiment, since we like kind of wanted to focus on like just the continuing learning setting. I do agree that like the forgetting issue is largely due to like lack of learning capacity, and multimodal models haven't like gotten to the scale of like GPT-3 yet, so we don't really have like many available models for us to test against. But like even the lack of capacity thing is like still a challenge, right? So we still need to design not just algorithms but also models that are able to like contain all the knowledge for each task within its parameters. But also, I think it might not just be due to capacity solely in terms of learnable parameters, because if you look at something like adapters, those are able to learn each of those individual tasks with a fraction of the learnable parameters, right? With like 2 or 3% each. So I'm not sure it's completely due to this learnable parameter issue or like learning capacity issue. There's also I think you have to like look at a combination of both improving the modeling side and the learning algorithm side.
Yeah, I absolutely agree. That was the point I was getting at, though, was that if you don't have that upper bound, it's hard to know. You might have this compounding effect, right, where it's just the forgetting was due to just insufficient capacity versus the forgetting being due to bad algorithm or not good enough algorithm.
Yeah, I guess it's hard to like tease out exactly what's causing the forgetting, because like the model and algorithm always kind of go hand in hand, right? Like you can't just evaluate the algorithm without completely independent of the model that you're training it on, unless you like do this for like multiple different algorithms and sorry, for multiple different models and see the same trends. But all the models are likely to be having like that same issue with the like limited learning capacity. But yeah, thanks for raising the point. That is an important perspective to look at this one.
Tyler, I see your hand is raised.
Hi, thanks for the interesting talk. So similar to Chris, I actually had a question, or kind of more of like a general question on your thoughts regarding task orderings. So in the paper that Chris mentioned from ECCV 2020, we actually found that organizing visual question answering stream by question type resulted in better performance than just giving like an IID data stream to the learner. And I noticed that in your experiments, you also found that different task orderings resulted in better performance. So I was kind of wondering if you had some ideas for different metrics or experiments that would be interesting to run to study why these different task orderings result in, better performance than some others. Like just kind of a more general question for your opinion or thoughts you might have.
Yeah, I actually had slides on the task ordering results as well, but I didn't include them for the sake of time. But yeah, as you pointed out, we do have experiments that show that task order definitely has an impact on how the model learns. So like for the people who haven't read the paper, the main finding there was, so in our experiments, we saw that like VCR seems to hurt the model performance at each turn. And then the finding in the paper, in our paper, was that if this if this hard task that's like ruining everything were to appear earlier, then it not only like performs bad after learning VCR, but also everything after VCR turns out bad as well. It's hard. Sorry. So was the question like why? Like, what are my thoughts on like why these tasks make a difference? Or
so I guess, part of it could be your thoughts on why it happened, but I was also just curious, since you've studied this multimodal continual learning setting, if you have any ideas for types of experiments or types of metrics that we could think about for better understanding why certain task orderings result in better performance, right? Like better understanding why does that VCR task hurt performance or something like that. It's kind of more of an open-ended question just to kind of understand your thoughts.
Yeah. So one thing about the CLiMB benchmark is that we have designed it so that like you just get these raw transfer numbers, and then you can kind of aggregate them in whatever you want. So in like whatever way you want. So one thing that we could look at is what is the average transfer of tasks if we like want to study a particular task, such as VCR, for example, then we can look at what's the average forgetting or average like upstream knowledge transfer of tasks before that are seen before VCR versus after if we try like 5 different task orderings, right? And so this would like kind of give us the so for example, if I were to see that task learned after VCR, or like task learned, or like if the fourth task that's learned, if VCR were to appear before it, is much worse than the fourth task that's learned if VCR were to appear after it, as an example, then that would like give me some insight into like VCR causing, or there being like some correlation with that VCR task and with that VCR task and like bad transfer afterwards. So I haven't thought too much about the task ordering side yet. Like so far, we were focused more on like building this benchmark and we're focused a bit more on some of the forgetting side issues or like challenges right now. But the task ordering challenge is definitely one that the community needs to be like thinking a lot more about. Like, how do we make these models kind of immune to the task ordering? Because task ordering is not something that we have any control over in the wild, right? Like when you encounter a new task, you just have to learn it. It's not like, oh, I'll find a more optimal task first. So we do want our models to not be as sensitive to the ordering, and there's like a lot of open research questions there, but I haven't looked into those personally too much yet. But I'm hoping to, of course, and I'm hoping the community does as well. Sorry, that was a bit of an open-ended response to your open-ended question.
No, that's okay. Yeah, it was a pretty open-ended thing. Thank you.
I'll finish with one last one, Tejas. Speaking off what you just said, how easy would it be for someone interested in this to grab your benchmark repo and add a new data set or a new model into it? Is that?
I'm hoping really easy, because one of our reviewers, like one of our nearest reviewers, all that they said in the review was like, your documentation is bad. So I spent 1 week of my life doing just documentation of the benchmark and nothing else.
Great.
So
anyone
yeah.
listening, you heard it yourself. If you want to play around, you have now well documented.
But if it's still confusing, just either drop me an email or raise an issue, and I'll look at it.
Great. So anyone interested, there you go. Continual VO. Well, I think this is a good time to wrap it up. Thank you so much.
Thanks a lot for having me.
Thank you so much, Tejas. This was a wonderful presentation.
Thank you.
Join us next week, same time, same place for our next